Having defined the Bayesian network, let's look at some of the reasoning patterns that the network allows us to perform. So let's go back to our good old student network with the following CPDs. We've already seen those, so we're not going to dwell on it. And let's look at some of the probabilities that one would get if you took this Bayesian network, produced the joint distribution using the chain rule for Bayesian network, and now computed, say, the values of different marginal probabilities. So for example, now we're asking what is the probability of getting a strong letter. And we're not going to go through the calculation because it's going to be tedious to sum up all these numbers, and I can just tell you that the probability of L1 is 0.5. But we can do more interesting queries. So we can now condition on one variable. Remember, we talked about conditioning a probability distribution, and ask how that changes this probability. So for example, if we're going to condition on low intelligence, and we're going to use red to denote the false value, and it's going to turn out that the probability, not surprisingly, goes down. It goes down to 0.39 because if the intelligence goes down, the probability of getting a good grade goes down, and so does the probability of getting a strong letter. So this is an example of causal reasoning because intuitively the reasoning goes in the causal direction from top to bottom. We could also make things more interesting. So we can ask what happens if we make the difficulty of the course low. And in this case, we have the probability of L1 given I0 and D0. And what do you expect the probability to do? Well, if it's an easy course, one would expect the grade to go up. And sure enough, the probability goes back up, and we're back to 50-50, more or less. Okay, so this is another example of causal reasoning, in this case with a little bit more evidence. You can also do evidential reasoning. Evidential goes from the bottom up. So we can, in this case, condition on the grade and ask what happens to the probability of variables that are parents or in general ancestors of the grade. So let's just imagine that this poor student takes the class and he gets a C. Initially, the probability that the class was difficult is 0.4, and the probability that the student was intelligent is 0.3. But now with this additional evidence, again, this is not surprising, the probability that the student is intelligent goes down by a fair amount, but the other alternative hypothesis that the class is difficult, also the probability of that goes up as well. Okay? So now, however, there is an interesting type of reasoning that is not quite as standard, and that is reasoning that is called intercausal, because effectively it's flow of information between two causes of a single effect. So remember, we had we're going to continue with the scenario before where our poor student gets a C, but now I'm going to tell you, wait a minute, this class really is difficult. So I'm going to condition on D1. And notice that the probability that the student is intelligent has gone up. It went up from 0.08 to 0.11. So that's not a huge increase. And as you'll see when you play around with Bayesian networks, that often the changes in probability are somewhat subtle. And the reason is that you have to, I mean, even in a hard class, if you go back and look at the CPD, it's kind of hard to get a C, according to this model, which is that the student gets a B. And so now we have that the probability of high intelligence still goes down. It goes down from 0.3 to 0.175. But now if I tell you that the class is hard, the probability goes up. In fact, it goes up even higher than this. Okay? So this is an illustration where this intercausal reasoning can actually make a fairly significant difference in the probabilities. So intercausal reasoning is a little hard to understand. I mean, it seems a little bit mysterious because after all, these are, I mean, look at these. You look at difficulty, you look at intelligence, there's no edge between them. How would one cause affect another? So let's drill down into a concrete scenario, which is this one, and just to sort of really understand the mechanism. So this is the most sort of purest form of intercausal reasoning. Here we have two random variables, x1 and x2. We're going to assume that they're distributed uniformly, so each of them is 1 with probability 50% and 0 with probability 50%. And we have one effect, one joint effect, which is simply the deterministic OR of those two parents. And in general, when we have a deterministic variable, we're going to denote it with these double lines. So in this case, there's only 4 assignments that have non-zero probability because the value of y is completely determined by the values of x1 and x2. And so we have these 4 distributions over here. And now I'm going to condition on the evidence y equals 1. Now let's look at what happened. Before I conditioned on this evidence, x1 and x2 were independent of each other, right? I mean, look at this, they're independent of each other. What happens when I condition on y equals 1? Well, we talked about conditioning. This one goes away. And we have 0.33, 0.33, 0.33, or rather 1/3, 1/3, 1/3. Okay? In this probability distribution, x1 and x2 are no longer independent of each other. Okay? Why is that? Because if I now condition on, say, x1 equals 0, then, okay, so actually before we do that, so in this probability distribution, the probability of x1 equals 1 is equal to 2/3, and the probability of x2 equals 1 is also equal to 2/3. Okay? And now if I condition on x1 equals 1, so now we're going to condition on x1 equals 1. So that means we're going to remove this line. And all of a sudden, the probability of x2 equals 1 given x1 equals 1 is back to being 50%. So it was 50% before, it went up to 2/3, and then if we condition on x1 equals 1, it goes back to 50%. And the reason for this is the following, if you think about it intuitively. If I know that y is equal to 1, there's 2 possible things that could have made y equal to 1. Either x1 was 1 or x2 was 1. If I've told you that x1 was 1, I've completely explained away the evidence that y equals 1. I've given you a complete explanation of what happened. And so now x1 is back to being the way it was before because there's no longer anything to suggest that it should be anything other than 50-50. So this particular type of interfacial name, because it's so common, it's called explaining away. And it's when one cause explains away the reason that made me suspect a different cause. And if you think about it, it's something that people do all the time when they're reasoning about, for example, in a medical setting, you're very sick, you think you're very worried, you don't know if you have the swine flu, you go to the doctor says, oh, don't worry, it's just a common cold. You don't know if you don't have the swine flu, but because you've explained away your symptoms, you're not worried as much anymore. Okay. Finally, let's go back to our example and look at an interesting reasoning pattern that is not, that involves even longer sort of paths in the graph. So let's imagine that we have the student got a C, but now we have this additional piece of information that the student actually aced the SAT. So let's see what happens there. Remember that when we just had the evidence regarding the grade, we had the probability that the student being intelligent was only 0.08. But now we have this additional conflicting piece of evidence, and all of a sudden the probability went up very dramatically to 0.58. Okay? What do you think is going to happen to difficulty? So now it's explaining away in action, going in a different direction, right? Because if it's not the fact that the student, if the student didn't get a C because he wasn't very bright, probably the reason is that the class is very difficult. And so that probability goes up. And so we have effectively, and we're going to talk about this, an inference that flows like that.